So the problem we have today is called the number of connected components in an undirected graph. And graphs are these really interesting data structures which have some really practical applications. So in this case, we have a list of edges with IDs, so these are just numbers. But imagine like each of these numbers could represent something in the real world. Like this could be a server, right? So you have a server 1 which is connected to server 2. And you have a server 2 connected to a server 4, or a server 3 connected to a server 4. Or it could even be something like a city, right? So we have a city 1 and we have a city 2 and we have a city 3. And let's say we want to represent, the flight paths between these cities or something along those lines. Then this shows a connection. So we have connections from city 1 to city 2, city 2 to city 3. So lots of interesting applications of this, just in general, with any kind of a graph. Now this is an undirected graph, as are these. There are some instances where you could have a directed graph. So something that goes from A to B, for example, is a separate connection, is a different edge, right? And you have something that goes from A to B and from B to A, but not vice versa. So maybe you have something going from A to C and you don't have anything going from C to A. That's a directed graph. But in this particular case, we just have an undirected graph. So let's take a look at the popularity of this question. So it looks like it's a fairly popular question, and recently been asked by a few companies. Okay, so that's good. So now let's take a look, a little bit closer look at the actual problem. So the problem says you're given the number of nodes and the edges, right? Number of nodes and the edges. And you want to find the number of components. So what are the number of components? So when you connect the nodes together like this, you end up with groups, right? So this is the first group right here. This is another group right here. And that's a component. So there's two components here. And in this case, because everything is connected to everything else, you just have one component. And so that's what we need, right? So our return is the number of components. That's what we want as the output. Now there are different approaches to this problem. Today I'm going to be looking at something that lends itself very well to this particular class of problem. And you can see how things are grouped here, right? So what that tells you when you have this kind of a grouping is you can use something called a union find algorithm. So union find is a very popular algorithm for problems of this class. And actually, I recommend going through this video by William Fizet. He has a few videos where he goes over the introduction as well as the actual implementation. I think they're really good quality. That's something I refer to. So I think it's definitely a good idea to go through those to get a background. And once you've done that, then let's start digging into the actual way it works for this particular problem and how we can solve it. So the steps that we're going to take is, first of all, we need to know like what are the roots of each of these nodes, right? So initially what we can do is we can create some kind of a list. Let's call it parent. And that list is just a list, 0, 1, 2, 3, 4. So what this means is that for each of these indices, it's the node is the parent of itself. So in this case we have 5 components, right? So if we have 5 components, so yeah, so the number of components is currently 5. Now as we group them though, so when we go group to 0 and 1, now we have group 0 and 1, so now we have 0, 1, and we have 2, 3, and 4. So now we have like 4 components, right? So here we have 4 components. And then when we group 0, 1, and 2, 3 and 4. Now we have 3 components, and 0, 1, and 2, 3, and 4. So now we have 2 components. So this is what we want to try and do. So how are we going to actually do this? So let's think about the actual logic. So first we have this list that we've created, which is good. So now let's define what our find is going to do, or let's actually start thinking about going through the list and doing some kind of a union. But if we're going to do a union, we also need to have a find operation. So if we're going through the list, we're essentially going through the adjacency, or sorry, the edges here. So 0, 1, and 1, 2, and 3, 4. So this is basically what we want to do. Our high-level algorithm looks like this. We have for each edge, we get the parent for the first node of the edge, get the parent for the second node. If they're disjoint, which means they're not already connected, then we will be connecting them. So we update the number of components by decrementing it by 1. Because remember, initially the number of components was equal to the number of nodes, right? 0, 1, 2, 3, 4, because they're not connected. Then we connect P1 and P2. And that's it, we're done, right? And at the end of this, we just return the number of components. And so this one doesn't talk about the optimization of path compression, but we can just do it without path compression. We'll take a look at both. So here's the general solution and the sort of the non-optimized solution. Initially, we get a list of, right? This is our 0, 1, 2, 3, and 4, right? We just get each of these as the parent. So each node is a parent of itself. And so that's why the number of components is n. And then we're going to be doing this right here. What we're doing here is we're going through each of the edges. We're getting the parent, right? This is our P1, getting the first parent, getting that second parent. And if they're not equal, so this is what this is the condition where it says they are disjoint. Then in this case, we want to decrement the number of components by 1, because we're going to be connecting to one node to another component, or just 2 nodes, or 2 components for that matter. So we're going to be combining them into 1 component. So we have one less component after this. And then of course we actually connect the roots. And so this will just update this array right here, and it says, you know, for this root, I want to set this is the root for this guy. And you notice here that we're doing a find operation. So that find is defined as a separate function. And by the way, this does not compress paths, sorry. So without the path compression, all we're saying is here's the node. First, just set it to the root, right? And we're trying to find the root. So while the parent of the root is not equal to this root, root is equal to parent. So all this is doing is, if you imagine, like if you have something like this, right? You have a parent, you know, 4, 3, 2, and your node n is 2 right now, and you're trying to find what the root is. Now the root is 4, but we don't know that, so we have to find it, right? So with this while loop, what it's saying is initially set the root to be equal to this node right here, then we check, is this equal to the root by looking in the array. If in the array, if it's the root node, then it will have the same value at this position. So here it doesn't. So we go up 1 level and we say, okay, make this the root. Is this the root? Nope, we're still not at that position, because the value 3 won't be at the position 3 in the array. And then when we come back here, we say, is this the root? And yes, it is, because the value 3 and the position, or value 4 and the position 4 will be the same, right, in your array. And so that's how we find it. And then we just return that. And if we try this out, we can see that it works, right? Now the problem is that it does not do path compression. So now, considering path compression, this is the same logic as before. The only difference is this within the find function, we have added this compression portion to it, right? So we set the root to n, we find the root. This is our finding the root, this part. And once we found the root, though, we don't stop and just return it. We also do some extra work to compress the path. So what we're saying here is if the root is not equal to parent of n, then we just want to basically, we want to basically update it. So as we're going up, if we have something like this, you have 2, 3, and 4. We don't just set 2 to 4. So we're going to set 2 to 4, but we're also going to add 3. So eventually we're going to have something that looks like this, right? That's what we're trying to do here. So while the root is not equal to parent of n, and n is whatever node, so we start from the bottom here, and we say, okay, I'm going to make this point to 4, but before I do that, I'm going to just save the current parent so that I can also update that parent. In this case, that's really a no-op because it's already connected to 4, but you can imagine there's like another parent to here. Let's say if the path looks like this, then first we're going to set 2 to 4, which is this right here. Then we're going to set 3 to 4, which is this right here. And then we're, 6, not 4. And then we're going to set 4 to 6, which is already connected, so that will be no op. So yeah, so as soon as we find that the root and the root is in fact the parent, we kind of stop. So that's what we're trying to do. So now we've optimized it while we're doing the find operation. And this is really the key. The compression is really what makes this algorithm very useful.